All right, so we're going to be taking a look at section 10.5 this time. Section 10.5 deals with conic sections. Now, you probably saw this stuff in pre-calculus with trig, so it may have been a little while. But what you may have been shown back then is that your conic sections can be described by intersections of a double nap cone with a plane. So we're going to be thinking about the different intersections that we could possibly get and when we intersect the double nap cone here with some sort of plane. And I'm thinking maybe let's start out with what would happen if we were to intersect the double nap cone with a plane that maybe is going to be intersecting it this way. So you would have maybe a picture that looks something like this. We'll chop off this part here, and we would end up with a picture that perhaps looks something like that. But if you were to take a look at this intersection head on, then you would expect to see maybe a picture that looks like that. This would be a parabola. Now keep in mind that this double nap cone just keeps going up forever this way and moving down forever that way. But this is not the only way that we can intersect the double nap cone with some sort of plane. So let's take a look at some other possibilities. One other possibility would be, let's suppose we intersect the double nap cone with a plane sort of like this. Well, if we do that, then we might get an intersection that looks like so. Now if you were to take a look at this intersection head on, then the intersection may look something like that. And this would be an ellipse. But there's still yet another way that we could intersect the double nap cone. Let's suppose that we take a look at intersecting this double nap cone with a plane more like this. So maybe the plane is going to chop this way, maybe chop this way. So you're going to have a piece that looks like this. You're also going to have a piece that looks like that. What we're getting in that case is a hyperbola. Now these are the three conic sections that we're going to be focusing on in this section. There are other conic sections that you could consider. In particular, one thing we could do is figure out what happens if we intersect a double nap cone like this with a plane through the vertex. And there are different ways that this could happen, but these types of intersections that we would get are referred to as degenerate conics. We're not going to really be worried about those in this section. We are, however, going to investigate each of these conic sections in turn. The first of which is the parabola. So let's think about what parabolas are. Well, let's start with the definition. So a parabola is a set of points in a plane So once again, a set of points in a plane that are equidistant from a fixed point that we're going to call F, and that's going to be what's referred to as the focus, and a fixed line that we're going to refer to as the directrix. So same distance, all the points that in the plane that are the same distance from this fixed point F called the focus, and this fixed point, or this fixed line that we refer to as the directrix. Now I'm going to make a claim here regarding the equation, or a standard form equation for these parabolas. Now an equation of the parabola focus 0, p, and directrix y equals negative p, is given to us by x squared equals 4py. But if we were to interchange the roles of x and y here, then we would have a different standard form equation, and this standard form equation would be y squared equals 4px. All right. Now, this is granted a bit of a special kind of case because we are assuming the focus is at 0, p, directrix is at y equals negative p. And you might be thinking that this equation, this x squared equals 4py, might be a little bit unusual because after all, we might be thinking about y equals ax squared plus bx plus c, where a, b, and c are constants and a non-zero, as sort of a standard form equation for a parabola. But what I'm going to do is I'm going to show you why we get this x squared equals 4py as the equation under these circumstances and based on this definition. So let's consider what happens if we draw a set of axes here. We're going to have the focus, that'll be our f, and it's located at the point 0, p. The directrix is y equals negative p, so we're going to take this to be our directrix. Once again, y equals negative p. And let's think about the fact that this point, the origin, is going to be the same distance from the focus as it is from the directrix. And that's important because the way the parabola is defined, it's a set of points in the plane that are equidistant from the focus and the directrix. Now, this point here is our vertex v. But we could also consider some other points that are the same distance from the focus as from the directrix. So for example, if I were to choose, let's say, maybe this point here, that looks like it's probably the same distance from the focus as directrix. And if I were to go the same distance but on the opposite side of the focus, I could plot a second point besides this one, plot its mirror image about the y-axis. And I could then draw, I have 3 different points on the parabola, I could draw the parabola through these. And we get a picture that looks something like this. All right, so we're interested in getting the standard form equation, which I'm claiming is x squared equals 4py. So in order to show that this really is the case, what we're going to do is take an arbitrary point on the parabola. And maybe this is the point we decide to settle on. We're just going to give it coordinates x and y. And if we go back to the definition of the parabola, the distance from f to this point should be the same as the distance from that point to the directrix. So we start to consider this definition once again. Parabola is the set of points in the plane, same distance from the focus as they are from the directrix. Now what that means is that this distance we see here had better be the same as the distance we see here. Now I'm going to label this point. Notice the x-coordinate from this point has not changed, but the y-coordinate, because it's on the directrix, is going to be negative p. The distance here is the same as the distance here. So we could use the distance formula for this piece, use the distance formula for this piece, and set the results equal to each other. But then we're dealing with radicals, and that's not probably very much fun. So we can use a little trick here where we just look at the squares of the distances, and that'll work out a little bit better for us in the calculations. So if we take the square of the distance here, set it equal to the square of the distance here, then we're in good shape. So you might ask, well, what is the square of the distance between the focus and this point here? We're going to take the difference in the x-coordinates, so that'll be x minus 0. We'll square that. We'll add the difference in the y-coordinates, squared, so y minus p, and that'll be squared. And that's the square of the distance between these 2 points. Now that's going to be the same as the square of the distance between this point and this point x negative p that's on the directrix. So once again, we'll take the difference in the x coordinates, that'll be x minus x, square that. Then we'll add the square of the difference in the y coordinates, so we'll have y minus a negative p, and that'll be squared. To clean this up a little bit, x minus 0 squared gives you x squared. Y minus p raised to the second power is y squared minus 2py plus p squared. On this side, you have x minus x, that's 0. Square it, you still get 0. We don't really need to write the 0 squared, and I guess really technically we don't need to write the 0 either, but just keeping it there. Y minus a negative p, that's going to be the same thing as y plus p, and we're going to be squaring that. We'll keep the left side as it is. And on the other side, we square the y plus p. Square your first term, gives you y squared. Multiply the 2 terms together and then double, gives you a 2py. And then square the last term, that gives you p squared. And then something really, really nice happens here. Because we'll notice that you've got a y squared term on the left side, a y squared term on the right side. Those are going away. You got a p squared term on the left side, p squared term on the right side. Those are also going away. So what you're left with is x squared minus 2py is equal to 2py. Now all I have to do to get this standard form equation is add 2py to each side, and that'll give us the x squared is equal to 4py. Keep in mind that this is based on the assumption that the vertex is at the origin. It's not always the case, obviously, that the vertex for our parabola will be at the origin. And so let's suppose that our vertex is at h comma k instead. Well, we can use some techniques from college algebra to modify this equation so that if the vertex happens to be, and I'll go ahead and just write this over here, if the vertex happens to be at hk, then our standard form equation here is going to change to x minus h raised to the second power is equal to 4p times y minus k. So in these cases where the vertex is not located at the origin, this is going to be really helpful for us. All we're doing is a horizontal shift here and a vertical shift there. So that's pretty nice. Now, the y squared equals 4px is going to be based on a diagram in which essentially this parabola is going to be, instead of opening upward, we could draw it so that it's opening to the right. We could have the focus over here, directrix over there, and that would be okay. The focus in this case would actually be at p comma 0, and the directrix would be x equals negative p. One other thing to point out is kind of important to keep in mind. The way that I ended up drawing this, p is positive. If the parabola had been opening downward, the focus would have been here, the directrix would have been up here, and p would have been negative. So if the parabola opens upward or downward, you're going to have p is either positive or negative, respectively. But in the case where your equation is y squared equals 4px, or maybe more generally, the square of y minus k equals 4p times the x minus h, if your parabola is opening to the right, then p is positive, and if the parabola is opening to the left, then p is negative. So we're going to be taking a look at finding the focus and the directrix of a particular parabola. Now, this parabola, we'll see in this example, isn't going to look too bad. Definitely seen worse. But we'll look at finding the focus and directrix. Find the focus and directrix of the parabola. we'll have y squared plus 10x is equal to 0. All right. Now, we are really just interested at this point in getting this equation more into a standard form like so. We're not going to have to worry about, in this case, the vertex being off the origin, so that's nice. But notice y is squared, x is not. We're going to be looking at a situation like this where you have a y squared equals 4px format. So let's go ahead and get started with this. We'll have y squared is the same thing as negative 10x. This has the form that we want. It's just that negative 10 is our 4p. So we can figure out what p is if we say that 4p is equal to negative 10. So p will be negative 10 fourths or negative 5 halves. We need to figure out where the focus is and where the directrix is, and this is going to tell us the information that we need. And so if we were to take a look at some sort of diagram where we end up drawing this parabola, let's see, we're going to have a picture looks something like the following. All right, so the vertex, once again, as I mentioned, is located at the origin. But with this equation being in the form y squared equals 4px, we're looking at a parabola that's going to be opening horizontally instead of vertically. But if p is negative, that means the parabola is going to be opening to the left. And the focus is going to be to the left of the vertex. In fact, 5 halves units to the left of the vertex. So our focus here is going to be at negative 5 halves, 0. The directrix will be on the opposite side of the vertex, but 2.5 units away. So if we were to draw the directrix like this, we would have x is equal to 5 halves as that directrix. And the parabola itself, well, you could just simply draw and you get a sketch. I'll just sketch it really quickly. It would, we're taking a look at a picture is going to look probably something more like that. So it's just going to open to the left, focus here, directrix there. Second conic section that we're going to be focusing on, no pun intended, is the ellipse. And so for your ellipses, you're looking at, once again, a set of points in the plane. But this time we're going to be looking at 2 different foci. For the parabola, we've got one focus. Here we're going to be looking at 2 different foci. So the sum of these distances from 2 fixed points, which we're going to call F1 and F2. Now these are going to be foci. And the sum of the distances is going to be constant. All right, so let's think about what this actually means for us. I'm not going to end up deriving the formula, but I do want to give you at least a little indication as to what this definition is entailing. So let's suppose that you have focus here, F1, and a focus here, F2. Now, an ellipse that we have might look something like the following. So when we say that the ellipse is the set of points in a plane, the sum of whose distances from two fixed points, f1 and f2, is constant, then what we're saying is that no matter where we are on this ellipse, if we were to take a certain point and calculate the distance from that point to f1, calculate the distance from that same point to f2, and add those distances together, that sum is going to be constant no matter where you are on this ellipse. So if I were to take a look at a point right here, for example, take a look at the distance from that point to f1, add the distance from that point to f2, and I'm going to get a certain constant. Now if I take another point, let's say that's right here, and I take the distance from that point to f2, take the distance from that point to f1, add those two distances together, I'm going to get the same constant that I got when I add those two original distances together. So once again, no matter which point you choose on this ellipse, if you take the distance from that point to f1, take that distance from that point to f2, add those distances together, you're going to get the same constant every single time. Now there's some other terminology that I'd really like to point out here. And let's maybe unclutter this just a tad. The way that I have this ellipse drawn, we've got the two foci here, f1 and f2. If I were to draw a line through f1 and f2, that line will intersect the ellipse in 2 points, v1 and v2. These points are called vertices. Now if I look at this chord that joins v1 to v2, that chord is called the major axis. So once again, the major axis is going to be the chord that joins the v1 and the v2. Now there's also a perpendicular bisector for this major axis, and if we take a look at that, intersection of the major axis with this line segment, with this chord, is going to give you the center of the ellipse. Also, this chord is what's referred to as the minor axis. So once again, we got the major axis that is the chord that joins the vertices together. Perpendicular bisector chord is going to be the minor axis. These two axes intersect at the center of the ellipse. Now, we're going to be taking a look at the standard form equation for an ellipse. And so let's suppose that we set up a note here, and we'll start out with one equation. We'll have the ellipse x squared over a squared plus y squared over b squared equals 1. So that's going to be our first equation that we look at for the ellipse. We're going to have a greater than or equal to b greater than 0. We certainly don't want a or b to be 0 here, giving us a 0 denominator. That's not good. But this is going to have foci located at negative c comma 0 and positive c comma 0, where c squared is equal to a squared minus b squared. The vertices are located at plus or minus a comma 0. So I'd like to go back to this particular type of diagram, but I'm going to be a little bit more specific with things. Let's suppose that we have our y-axis here. Let's suppose we have our x-axis here. Center, that's at the origin. And so we're going to start to think about what the A, B, and C are going to really represent here. So the claim is that the vertices are located at a comma 0 and negative a comma 0. All right, well, if you think about what that means, what it means is that the distance from the center to each vertex is going to be a units. Also, the claim is that the foci are located at plus or minus c comma 0, where c squared is a squared minus b squared. And I'll give you an indication as to why we have this relationship between a squared, b squared, and c squared. But what we know right now is that the distance from the center to each focus is actually c units. So what I would like to do is think about the definition that we have for the ellipse first off. And I want to consider this particular point, this vertex, V2. And once again, I'm claiming that V2 has coordinates A0, and then V1, which is right there, will have coordinates negative A0. But one of the things that we know about each point on the ellipse is that if you take the distance from that point to focus, let's say F2, and add the distance from that same point to the focus F1, you're going to get the same number every single time. Well, if you think about the distance from V2 to F2, that means that this distance is covered once. You take a look at the distance from V2 to F1, it means that this distance right here is covered again, but the distance in between the foci is also covered. So you've got this distance covered twice, this distance covered once, this distance covered 0 times. But because of symmetry, we know that if this distance is covered twice, then that's equivalent to this distance being covered once and this distance being covered once. We know the distance between the foci is covered once. We also know that the distance between the two vertices is 2 times a. That major axis has length 2a. We know this because the distance from the center to the vertex is a units, and the distance from the center to this other vertex is also 8 units. Also, take a look at the coordinates. X, Y, you're going from negative a to positive a. That's a total length of 2a. All right, so no matter which point that we choose on this ellipse, if we were to take a look at the distance from that point to F1 plus the distance from that point to F2, we're going to get 2a every single time. In particular, this is true if you're looking at one of the endpoints of the minor axis. And this is kind of important for us to keep in mind, because if you take a look at the distance from this endpoint of the minor axis to F2 and the distance from that same point to F1, you'll notice these two distances are actually going to be exactly the same. Now, the reason we know this is because this minor axis is a perpendicular bisector of the major axis. Well, if we know that the distance here plus the distance here is 2a, and we know that these two distances are the same, then that implies that the length here is going to be a. We also have the distance from the center to the focus is c, but we also have one other thing that I haven't mentioned yet, and that is the length of the minor axis is actually 2b. So the distance from the center to an endpoint of the minor axis is b. You've got a right triangle sitting here. Two legs are length b and c, hypotenuse has length a, and so we know that a squared is equal to b squared plus c squared. But if you want to solve for c squared, you'll subtract b squared from both sides of the equation. You'll have c squared is equal to a squared minus b squared. Now, this is one possibility that we have for a standard form equation, but once again, we're being really specific here because the center of this is located at the origin. Now, let's think about what would happen if instead of the major axis being horizontal, maybe the major axis is vertical. Well, that's going to change our equation just a little bit. We'll have the ellipse x squared over b squared minus, y squared over a squared is equal to 1. We still have this relationship that a greater than or equal to b greater than 0. Now, the foci will be located, instead of plus or minus c0, they'll be located at 0, plus or minus c. We'll still have this relationship between a squared, b squared, and c squared, but the vertices will be located at 0, plus or minus a. So that's pretty good. Now let's go ahead and write some of this out. We'll have, once again, a relationship between a and b. Foci are at 0, comma plus or minus c. C squared still a squared minus b squared. And the vertices are located at plus or minus a, comma 0. Now, to give you just a slight variation of what's going on here, let's suppose that the center is located at hk instead. Now, if we were to go back to, let's say, this equation here, what that would turn into is x minus h quantity squared over a squared plus y minus k squared over b squared is equal to 1. So once again, if the center is off the origin, we can do the shifts like we do in college algebra and still get a standard form equation. The only difference between what we would get going from here to there with this transition is the b squared would be here and the a squared would be there, and that would be just fine. Not a big deal at all. All right, so let's take a look at some examples. In fact, what I'm really interested in is how we draw these ellipses. So consider the following example. Let's sketch the graph. And we'll have 9x squared plus 16y squared is equal to 144. Now clearly this is not a standard form equation, but it doesn't take very much to get it in that standard form that we want. Main thing we have to be mindful of is let's go ahead and get the right side, whether it's this form or this form, right side is going to be 1. And so we can think about dividing both sides of this equation by 144. Okay, well if we divide 9x squared by 144, then what we're going to get is x squared over 16. And if we divide 16y squared by 144, we'll get a y squared over 9. 144 divided by itself, of course, gives us 1. So this means that our a squared is 16 and our b squared is 9. Notice the number underneath the x squared is larger. So a squared is 16, which means a is 4. B squared is 9, so we're going to use b equals 3. Keep in mind though, going back to what we have in this diagram, the distance from the center to the vertex is a units. The distance from the center to an endpoint of the minor axis is b units. This particular standard form equation indicates that the vertex, the center is located at the origin. Alright, so once again, the center of the ellipse is at the origin. And basically what we do is from the center, we take a look at what's underneath the x squared. Now that 16 is a squared in this case. Square root of a squared, square root of 16 gives us 4. So from the center, we're going to move left and right 4 units. So right 4 here, left 4 there. 16 is associated with the x squared. So that's what we're going to do, is we're going to take the square root of 16 from the center, move left and right 4 units to plot our points. Now these are going to be the vertices of this given ellipse. We then take a look at the 9 that's underneath the y squared. Square root of 9 gives us 3. So from the center, we're going to move up 3 units and down 3 units, and we'll plot those points. Now just do the best you can. Just do the best you can to draw the ellipse through these different points. It doesn't have to be perfect. This certainly won't be. But just do the best you can. So that gives us an idea of what the ellipse with the given equation looks like. Not really too worried about drawing the foci. I can use the information here to get the endpoints of the minor axis as well as the vertices and just draw the curve through those locations. So that's pretty convenient. Now, second example that I'd like to do before we move on to hyperbolas is we're going to find an equation of some ellipse. And some information about that ellipse will be given, which is good. Otherwise, they're probably pretty difficult to figure out the equation of the ellipse. So here we go. Find an equation of the ellipse. And for this particular ellipse, we're going to have foci 0, 2, and 0, -2. And we're going to have vertices at 0, 3, and 0, -3. Now notice that the vertices and the foci are actually going to be the same distance from the center, but when we have plus or minus 3 here and the plus or minus 2 here, that's going to indicate that the center is located at the origin. Now the vertices are going to be above and below that center, the foci, same story, above and below the center. And so with that in mind, we'll just go ahead and draw a quick sketch here. You'll have your foci labeled, maybe F1 here, F2 there. You'll have V1 there and V2 there. So the major axis is vertical this time. It was horizontal here. So the a squared is actually going to be under the y squared this time, given that the major axis is vertical. Now a is the distance that each vertex is from the center of the ellipse. So we know now that a is equal to 3. Foci are c units away from the center, so we know that c is equal to 2. But we also know that c squared is a squared minus b squared. And it's that relationship between a, b, and c that will enable us to figure out what b is. But we're really, quite frankly, just interested in what b squared is so that we can plug it into the equation here. So the c squared gives us 2 squared, a squared is 3 squared. That's going to give us 4 is equal to 9 minus b squared. And so with that in mind, your b squared will be 5. All right, so we have b squared. We also know that a squared is going to be 9. And when we take a look at our standard form equation for the ellipse here, what we're going to get is, well, x squared over b squared will be x squared over 5. We'll add y squared over a squared, which will be y squared over 9. And then our right side is equal to 1. So that's our equation for this particular ellipse. Now the last part of this section deals with hyperbolas. All right, so let's consider what's going on with these hyperbolas. Well, for the hyperbola, we're once again looking at the set of all points in a plane, but this time we're looking at the difference of whose distances from two fixed points is a constant. Right. So now instead of looking at the sum of the distances from a point to each focus, we're now looking at the difference of those distances. And I guess one might say, let's look at the absolute value of the difference of the distances, and that number is going to be constant for every single point that's on the hyperbola. So you still have this idea of two foci. And the way I'm going to draw this is, let's say we have focus F1 here and a focus F2 here. Now the way this is going to work is you're going to have one branch of the hyperbola, say it's going to be going this way, and the other branch of the hyperbola, let's say, is going to go this way. All right, so if you take a look at the line that passes through F1 and F2, notice that that line actually intersects the hyperbola in two different spots. You can probably guess what these points are called. They're called vertices. So we're going to call these V1 and V2. Now for now, I'm going to go ahead and erase these parts here. But I do want to still keep the little line segment that joins V1 and V2. That line segment is horizontal. Notice that if the line segment that joins the vertices is horizontal, it turns out that our branches of the hyperbola are going to open left and right. But it could be that the line segment joining the vertices is vertical, in which case the branches would open upward and downward. But this line segment that we have joining these two vertices is what's referred to as the transverse axis. Once again, it's called the transverse axis. Now, some of this terminology you're going to see when you look at the solutions to the recommended exercises. Now, the midpoint of the transverse axis is what we refer to as the center of this hyperbola. Okay, but I'm going to erase this now. Don't really need it for what I'm about to show you. Let's go back to the definition of the hyperbola. Set of all points in a plane, the difference of whose distances from two fixed points, F1 and F2, is constant. Now, if we were to take a certain point on the hyperbola, let's say we take this point right here, and we consider the distance from that point to F1 and the distance from that point to F2, let's consider the difference in those distances. So if we were to take this distance here minus this distance here, we're going to get a certain number. But if we were to choose, let's say, a different point, maybe we decided to choose this point on the hyperbola, and we decide to take the distance from that point to F1, take the distance from that point to F2. If we were to take this distance minus this one, we would still get the same constant we got before. Now, one could argue that we're interested in taking the distance from a point to F1 minus the distance from that same point to F2, in which case you would have a positive here and you'd have a negative there because this distance is actually shorter than this one. So that's what I was mentioning earlier, is maybe we're interested in looking at the absolute value of the difference of these distances. But if you take the order right with the differences, it's not going to matter either way. You'll still get that same constant every single time. Now, here's what we're going to need to do. We're going to need to take a look at the standard form equations for the hyperbola. And what you'll probably find is that these standard form equations look very similar to the standard form equations for the ellipse. And then we'll take a look at how to draw these different hyperbolas. And then the section will be finished. So, let's consider the following note. Hyperbola we're going to be looking at here is going to have equation x squared over a squared minus y squared over b squared is equal to 1. So the big difference that you're noticing here is a minus here instead of a plus when looking at the hyperbola's standard form equation versus the ellipse's standard form equation. This is going to have foci at plus or minus c comma 0. This time c squared is a squared plus b squared. So that'll be the relationship between a, b, and c here. The vertices will be located at plus or minus a comma 0. And asymptotes and these asymptotes are going to be y equals plus or minus b over a times x. All right. Now, where the asymptotes come in is that we're looking at long-term behavior of the graph of the hyperbola. Now, let's suppose that instead of the x squared over a squared having a positive associated with it, maybe it's the y squared over b squared that has the positive associated with it. So we'll look at the hyperbola. And so this time, once again, you'll have the y squared is going to be positive. So you'll have y squared over a squared minus x squared over b squared. Still going to have 1 on the right side. This is going to have foci. Instead of plus or minus c comma 0, you're going to be at 0 comma plus or minus c. Once again, c squared is a squared plus b squared. You'll have vertices at 0 comma plus or minus a. And also you'll have asymptotes here, not a huge surprise, I would suppose. And those asymptotes will be y is equal to plus or minus a over b times x. So what I'd like to do is give you an idea of how we might go about drawing a graph like this. So if we have x squared over a squared minus y squared over b squared is equal to 1, let's consider that the center is going to be located at the origin. We're going to move a units to the left and a units to the right. And those are going to be the locations of our vertices. Now, if this were our equation instead, then those vertices would actually be above and below the center. But here, using this equation, the vertices will be left and right a units from the center. Now, what we're going to do at this point is we're going to form a rectangle. And to form this rectangle, we move a units left of the center, a units right of the center. But we're also going to move up b units, and I'll put a little x there to mark the spot. And I'll put another x here to mark the spot. This will be at b and at negative b. We'll draw a rectangle in the following fashion. The rectangle is going to have a height here of 2b and a width of 2a. So we end up using this rectangle essentially as sort of a guideline for drawing the hyperbola. Now, take a look at the diagonals of this rectangle and then extend them. Now, if we take a look at those diagonals and extend them, keep in mind both of these diagonals are passing through the origin, so the y-intercept is going to be 0, 0. But if you take a look at the slope, for this line, the rise is b, the run is a. So the equation for this line would actually be y is equal to b over a times x. The equation for this line would be y equals negative b over a times x. Those are precisely the asymptotes for our hyperbola. What's more, when we go to draw the hyperbola, this is going to open left and right. We're going to approach those asymptotes. Those are going to give us the long-term behavior. And to indicate why that gives us the long-term behavior. Let's think about the equation that we have here, this x squared over a squared minus y squared over b squared equals 1. Now, here's what we have to consider, is that x squared over a squared is the same thing as 1 plus y squared over b squared. But a and b are going to be fixed. But as x and y both increase in absolute value, so as x grows or decreases without bound, and as y also grows or decreases without bound, then what we're going to get here is that x squared over a squared is going to be approximately the same thing as y squared over b squared. So for sufficiently large x and y in absolute value, we're going to have x squared over a squared is approximately the same as y squared over b squared. Now, if you think about that, that means that your b squared over a squared times x squared will be approximately the same thing as y squared. So if you were to take the square root of this side and the square root of this side, you'd have plus or minus b over a times x approximately equal to y. And so asymptotically, as x and y get sufficiently large in absolute value, y equals plus or minus b over a times x will be the asymptotes for this graph. Now, let's take a look at two examples. I do want to point out before I get into this next example that we can also do the shifting that I was mentioning before for the parabolas and also for the ellipses. So if we wanted a center other than the origin, we could always change, let's say, this to an x minus h in parentheses squared, change this to a y minus k in parentheses squared, and do similar things down here if this happens to be what our equation needs to be based upon. All right, so let's apply what we've learned over here to do the next example. We're going to sketch a graph of 9x squared minus 16y squared is 144. Divide both sides of this equation by 144, and we'll have x squared over 16 minus y squared over 9 is equal to 1. We can go back to this idea. We know that with the positive associated with the x squared part, that the hyperbola is going to open left and right. Center is going to be located at the origin. And so from the center, we're going to move 4 units, because the square root of 16 is 4, we're going to move 4 units to the right, 4 units to the left, and those will be the vertices of our hyperbola. We'll also mark a spot 3 units above and 3 units below the center, because square root of 9 gives us 3, and that's associated with the y squared. We'll use these points to draw a rectangle. And then we'll extend the diagonals of this rectangle, and those will be the asymptotes for our hyperbola. Now, to make this stand out perhaps a little bit, I'll draw the hyperbola in a different color. Vertices are sitting in these locations. The hyperbola is opening left and right, so we'll let the graph approach these asymptotes. And it doesn't have to be perfect, once again. Just have to get an idea of what the curve looks like. So that would be a sketch of the graph of the given equation. Now, the last example that I'm going to show you here is going to involve a hyperbola whose center will not be at the origin. Now, the equation isn't going to look very nice either. But we'll sketch the graph, sketch the conic section, we'll have 9x squared minus 4y squared minus 72x plus 8y plus 176 is equal to 0. All right, so that'll be our equation. Looks absolutely nothing like one of our standard form equations, but that's quite all right. I'd like to rearrange the terms just a little bit. Put the 9x squared and the negative 72x together, put the minus 4y squared and the 8y together, and I'm going to go ahead and subtract 176 from both sides of this equation. Now, if we were to factor a 9 out of both of these, I'm going to leave some room here because we're going to complete the square. That's what's happening. So we'll have 9 factored out. We'll have x squared minus 8x. Factor out a negative 4 here. We'll have a y squared minus 2y. And then we'll have the negative 176. And then we'll see what else we have to add to that right side. Well, the x squared minus 8x, within the parentheses, we're going to, once again, complete the square. Within the parentheses, coefficient of x squared is 1. Coefficient of x is negative 8. We'll take half of that, which is negative 4, square it, and that'll give us 16. Now, what's happening at this point now is we'll have 9 times 16 that just got added to that left side. So we'll have a 144 that's added to that right side as well. We've got to keep everything balanced. Now on this side, within the parentheses, we have a y squared minus 2y. Coefficient of y squared is 1, that's good. We're going to take half the coefficient of y here, which is negative 1, square it, you get 1. While we added 1 within the parentheses, we actually subtracted 4 from that left side because that 1 is multiplied by negative 4. You subtract 4 from the left, you need to subtract 4 from the right side. So we go back, take a look at the perfect square trinomials. X squared minus 8x plus 16 is the same thing as the square of x minus 4. The y squared minus 2y plus 1 is the same as the square of y minus 1. And then if you take a look at negative 176 plus 144, that's going to give you a negative 32 minus 4 gives you a negative 36. This is actually set up pretty well because at this step we can divide both sides of the equation by negative 36. Now 9 divided by negative 36 is going to give you a negative 1/4. So we'll have a negative x minus 4 squared over 4. Negative 4 over negative 36 is going to give us a positive 1/9, so we'll have a plus y minus 1 squared over 9. And then dividing the right side by negative 36 gives us 1. So notice that the positive is actually associated with the y part and the negative is associated with the x part, and that means that our hyperbola is going to open up and down instead of left and right. Also, with the x minus 4 squared and the y minus 1 squared, we know the center of this hyperbola is going to be located at 4, 1. From that center, this tells us we're going to have to move left and right square root of 4 or 2 units from the center. And this tells us we're going to have to move up and down 3 units, or square root of 9 or 3 units. And those will actually be the locations of our vertices. So let's see how this all unfolds. Once again, center is going to be at 4, 1. So we'll draw. It's 1, 2, 3, 4, 5. Again, center, 4, 1. So we'll put that right there just to mark the spot. We're going to take a look at this y minus 1 squared over 9 first, because once again, the hyperbola is opening upward and downward. Square root of 9 gives you 3, so from the center, we're going to move up 3 units. That'll be one vertex. We'll move down 3 units. That'll be the other vertex. Also, with the 4 associated with this x part, square root of 4 gives us 2. From the center, we'll move left 2 units, we'll move right 2 units, and once again, X marks the spot. We're going to use these 2 points and these 2 X's to draw our guiding rectangle. Now, we draw the extended diagonals. We have the vertices listed here and there. And next step is to draw the hyperbola using these extended diagonals as asymptotes. And so what you're seeing in purple is just a sketch of this hyperbola. And that's an example of how you can draw one of these things if the center is not located at the origin. And that finishes 10.5. So we're going to give you some recommended exercises. And these exercises are 1. All right, so we'll take a look at some recommended exercises. We'll have 1, 5, 11, 15, 17, 19, 25, 31, 37, and 43.